And let me welcome once again our speaker, who is Steve Oberlin. Steve is currently the CTO for accelerated computing in NVIDIA, a position he took up in 2013. One of his responsibilities is to oversee the development of NVIDIA's flagship GPUs for modern high-performance computing, providing the infrastructure and the tools that have made modern machine learning such a dynamic and impactful discipline. Steve is a computer engineer at heart. In 1980, he joined Cray Research, where he first worked on the design of the early vector machines, and then later on became the leading figure behind Cray's first massively parallel supercomputers. He holds 14 US patents that date back to this time. They cover many deep technical aspects of Cray's supercomputers, but also include the ornamental design of one of their computer cabinets. In his talk today, Steve will bring together these two threads in his life. He'll talk about the relationship between high-performance computing and artificial intelligence, and tell us what the symbiosis means for the present and for the future of scientific simulation. Steve.
Thank you, Philip, and I'm starting sharing. So this is the point in time where we hold our fingers, and excellent. Let me know when you can see the slides.
We can see them full screen, perfect.
Awesome. Okay, so thanks again for the opportunity, and I'm happy to see so many people joining after the fiasco last week, for which I apologize, and I'll try to make it up to you. I'm hopeful that this will be interesting and at least somewhat new information, and you'll find it worth the extra patience to bear with me. So let's just talk a little bit about really the purpose of the computers that I've spent my career working on, supercomputers. And going back in time to the invention of computers, people have been using them to simulate physical phenomena. I mean, in the earliest days, mechanical computers were used to compute ballistics, and since then it's been across all domains of science. And I recognize I'm speaking to physicists and acknowledge that all domains of science really are physics all the way down. So simulation has several advantages over pure theory and direct experimentation. It can be a way to study implications of theory and explore behavior of systems that resist direct experimentation, really too large phenomena, too small, too dangerous, things that take too long to experiment with or happen too fast. And the classical method for the past 60 years has been to, and by classical, I mean like numeric method, not using things like cellular autonoma. It's been to create mathematical models, typically systems of partial differential equations that are encapsulating the theory or the physical laws, set initial and boundary conditions, and then repeatedly solve those PDEs. The big problem here, and it's been an opportunity for me, has been that PDEs are really monsters to solve, and the approaches that people have to take for problems that have many degrees of freedom is to discretize the space that you're simulating, represent everything with a fine mesh of points where each point is encoding in some way all the properties of the model, and then do this approximation where you evolve the model over many tiny steps in time, doing finite difference or whatever to arrive at some prediction eventually of how the model is going to look in the future, or how it would have looked in the past. And this has several implications. One, it's incredibly computationally intensive, and also iteration that's sort of inherent in many of the algorithms demand high numerical precision. So double precision floating point has been the typical requirement for all supercomputers, 64-bit floating point. So very demanding on the hardware. And in the end, you're able to predict a number of measurements and extract information from your system that you've evolved. Evaluate behavior of systems and measure forces or theoretical forces on model elements, and do things like calculate drag or pressure, velocity, and so this makes simulation really useful as an engineering tool. But because it's very difficult and computationally intensive, it has really required the largest supercomputers in the world. And nobody, in my experience, has ever been satisfied by the size of the problem that whatever the extent capability is of supercomputers, of the problems that they can solve, their simulations. And really it's this insatiable appetite that has driven HPC, for the 40 years I've been involved in it, 40 plus, and really all the way back in time. And I expect into the foreseeable future we'll continue to drive it, however short that period of time might be. So just a personal perspective, this was a quote that I saw fly past on Twitter, and unfortunately I didn't pin it. I lost it, so I don't know who to attribute it to. But it's essentially making a statement about the difference between science and engineering, with a little bit of a mad twinge to it, which I appreciate, because I identify as an engineer, but I appreciate science and what scientists try to do. My role is as a tool maker. I build tools for scientists and engineers, and a good tool maker has to understand at least what people want to do with the tools and try to study the problems that they're facing and anticipate those. It's a little bit like being a luthier, someone who makes guitars, not typically the same set of skills as a master virtuoso guitarist, but you should at least be able to plink out a tune. And that's probably not a bad analogy for myself. And as I said, what people want and need is pretty much, in the supercomputing world, always about an order of magnitude more than what they have. And when they do get 10x, they just turn around and grow their problem 10x, because there's just so much more precision and scale, and there's always more to apply the tool to. So there's this enduring law of conservation of exponential demand and capability, where the capability is always struggling to keep up. And I think this is what makes me a mad engineer, because exponential growth over long sustained periods of time is really unprecedented, and it's kind of a mad business. So people are to sort of appreciate how mad it is. I think it's fun to think about orders of magnitude, and humans really aren't evolved to think about the world in exponential terms. And my illustration that I like here is to just illustrate 3 orders of magnitude in terms of approximate speeds achievable by various forms of human locomotion. And even making a transition, if you're existing in just one of these stages and being able to make that order of magnitude transition to the next stage, that's a very distinct qualitative change in your life, much less thinking about 3 orders of magnitude. And the reason I'm illustrating 3 is because in the supercomputing world, we're driven by these prefixes, by giga, going from mega to giga, and giga to tera, and tera to peta, and those leaps that we mark as milestones in the supercomputing world are 3 orders of magnitude. And the difference in 3 orders of magnitude, when you're living it each step of the way, you kind of don't see that. But if you want to compare, crawling from Los Angeles to New York versus flying from LAX to LaGuardia, very different endeavors completely. So over my career in 40 years, so the Cray 1 was the first supercomputer I laid hands on in 1980. This was a 160 megaflops peak performance system. And the most recent computer I had anything to do with was Summit, which was went online in 2018 and became the #1 fastest supercomputer in the world at 200 petaflops. That's 9 orders of magnitude, which is mind-boggling. And to try and put it in scale over 40 years, if you had fired up the Cray 1 and just had it running flat out from 1980 until 2020, it would have basically completed 1 second's worth of computation for Summit, right? It would have, because it's basically 40 years if you work the numbers. And I did this for my wife. She was asking about what an exaflop meant, and I said it's 10 to the 18th, and she said, how big is that? And so I just kind of did the numbers. It was around the time we just had our 41st anniversary or something. So 40 times 365 days times 24 times 3,600 seconds, that got me to 10 to the 9th seconds. And so I needed to express it in terms of nanoseconds, and in order to get to 10 to the 18th. So I told her we'd been married 10 to the 18th nanoseconds, which is just a little bit over an nanosecond. And she, of course, replied that it felt more like 10 to the 19th to her. But the scale of the advance that's been made is it's hard, even for me, having lived it, to look back and integrate it. But really, it's sort of like that discretized problem that we're trying to simulate. At any point in time, you're looking ahead and calculating the slope to achieve the next performance step, and often that requires an architecture change or advance. So like going from the CPU only 7600 to the Cray 1, inherently a 10x. Part of that was clock speed, and part of it was the addition of vectors. I was one of the designers on the Cray 2, and going from the Cray 1 to the Cray 2, part of it was clock speed again, but then we were also going multiprocessor. And so each of these steps kind of involved a bit of a paradigm shift. And similarly, going from the vector systems to MPP, distributed memory computers based on microprocessors, that was a really large disruption because it wasn't just tweaks to the applications. It really involved rewriting your applications using MPI for microprocessors that were heavily dependent on caches for their performance and very weak interconnect compared to what people were used to. The T3D and E were much better than the clustered commodity systems that kind of inherited this whole MPP space. But it had the advantage of putting us on a Moore's law curve, and or really being rushed along by Moore's law without having to really do too much over the next 10 or 15 years. And this is a chart then showing Moore's law. And so the T3D was introduced in this 1993 timeframe. And the top line here basically is showing you transistors. And you can see we're still getting basically Moore's law increase in the number of transistors, but pretty much around the middle of the 2000s, things dramatically changed. Until that point, we were pretty regularly getting a 2x every couple of years, and this was a fairly long period of stability, almost 10 to 15 years. And the thing that broke first was, we every generation reduced the power supply voltage for these CMOS devices. They started out at 5 volts, and then with every generation it was reduced until basically we couldn't reduce it anymore because we would have lost the gap that we need for transistors to switch properly. The voltage around 0.9 volts and 1 volt to 0.9 volts is starting to approach the switching threshold for the transistors when things get kind of nonlinear and power goes up, etc. But a second thing was happening, and so that was called the end of Dennard scaling, and that started hitting in here, and we started power capping and frequency capping how fast we could toggle transistors, and single thread performance basically started to level out. But this was also the point where we sort of ran out of computer science to pour into accelerating CPUs. Now, all of the architecture tricks that we use to analyze instruction streams and issue lots and lots of instructions, we had reached a point where pouring more transistors into a single core, this bottom line is the number of cores, was no longer really producing the kinds of performance improvements. And so this was the point where single chips went multi-core. And so something qualitatively different started happening right there. We still were on this 2x plus 2x plus 2x kind of path, and multi-core made it maybe a little trickier for people to try to completely utilize a multi-core CPU if they really wanted to apply it all to a single thread. But actually the pattern that people were using for their distributed applications was to have an MPI rank. MPI was the parallel communications library that basically became the de facto standard with the adoption of massively parallel processors. And so an MPI rank basically was kind of one chunk of work and distributed memory and a core. So one core a couple gigabytes of memory and one network interface was sort of what a lot of people used as a rank size, and you could just distribute that across cores. So that helped us continue scaling. And also at about that same time, then we saw the very first in 2007, just a couple of years after the first multi-core CPUs arrived, we had the first CUDA capable GPUs that were introduced. And GPUs are fundamentally something different. And I'm not going to spend a lot of time talking about, the too much of the backing of this and the details around GPU accelerated computing. There's lots of good information out there. But GPUs, because they're, they have an embarrassingly parallel heritage coming from the graphics world, where essentially the task is determining visibility of billions of polygons per second and shading them and painting billions of pixels per second, and all of those things being basically independent activities that all were basically executing slightly different branches of the exact same program, enabling really investment of very little power into the control and allowing the ability of to just really replicate these execution pipelines that were not latency sensitive, instead had deep latency hiding capability. And so these throughput processors could be paired with CPUs, they're accelerators, and that heterogeneous architecture, if you modified your code to take advantage of the GPU, offload that 5% or whatever of the lines of code in your application that ended up comprising 95 or more % of the cycles of the code. If you could offload that, you could see a nice 10x or sometimes more. And so that's kind of the current state of things today, and why pretty much all of the fastest supercomputers, with just a couple of exceptions, are accelerated these days, and all of the most efficient ones in terms of flops per watt are definitely accelerated because of the tiny fraction of power that has to go into control. So this is the top 500. The top 500 list, started tracking this in the early 90s with the MPPs. And it's basically, unlimited LinPack and, not too much different than just, measuring the peak performance of the assembly of hardware, but it does impose some ability to compute and communicate. But it's basically the way that we track supercomputer performance. So it's the top 500 systems in the world, sorted by performance, and you can see the number one line is this middle one, and it's kind of stair-steppy because it's single systems, and sometimes a system will persist at the top for a few publications of the list, which comes out twice a year. The top line, and this is of course a log scale. When you work in an exponentially growing industry, you end up using a lot of vertical log scales. This is the sum of all 500. And this is number 500, the smallest system. And you can see that this is a remarkably straight line, which it should be on a log scale over many, many years. And at the bottom of it, LinPack number of number one, I'm tracking these here, is 100 gigaflops. So this is already 3 orders of magnitude faster than the Cray 1. And pretty regularly, we saw LinPack in the #1 systems achieving a 10x improvement over the priors. But you can also see that as we get out here, into 2010, that extrapolating these as straight lines, that we're starting to encounter trouble, right? We're no longer scaling at the same rate. The Dennard scaling has failed us. We're starting to see scaling issues that are affecting the ability to use all of the transistors. Wire scaling is gotten very bad. We're still getting pretty good dynamic power scaling, and leakage current is scaling reasonably well, but the ability to wire everything up is a problem. And the dynamic power is really only scaling at about half the rate that it would need to in order to not see devices increasing in power. So one trend, if you look back in history and if you plot forward, you're going to see that compute devices that are being used for performance and being clocked at their maximum speeds are going to continue to be more and more power hungry. And we should have seen a supercomputer surpass 100 petaflops in 2015. And in fact, it was Summit finally in 2018 that did that. If we had stayed on the straight and narrow, we should have seen an exaflop in 2018 instead of 100 petaflops. We're probably going to see exaflops systems in the next year or two at the outside. But it's getting progressively more expensive, huge amounts of power, and I'm predicting that in 10 years, this line is going to be pretty flat. And so, slight diversion into AI land around 2012, 2013, somewhere in there. We started to see GPUs and deep learning algorithms make a comeback from the dead after a couple of nuclear winters. And it started first with them being trained, AlexNet and ImageNet being trained to do image recognition and segmentation. But quickly, the zoo of neural network types proliferated, and we started seeing them being endowed with memory and reinforcement learning, giving them the ability to drive toward goals over time, to become generative, so that not just classifying things, but actually starting to generate new images or make predictions that are actually, what's the next video frame going to look like? Huge steps in natural language processing, et cetera. And this has turned into this all is yet another proof point that it's way more important to be lucky than good, because NVIDIA was just in the right place at the right time. It turns out that a lot of graphics algorithms that are used to paint billions of pixels extremely quickly, all of those calculations are matrix multiplies, and that's the fundamental unit of computation, basically, for neural networks. And we already had libraries. We'd already had CUDA out for probably 7 years before Alex Krasinski did AlexNet, and all GPUs, even the gaming GPUs, were CUDA capable. So it was a real democratization that just made GPUs in the right place, which was everybody's computers already, at the right time, which was when there was an enormous amount of data, and the algorithms, most of them already existed from from many years before, but without the computational horsepower and the data, the neural networks just weren't capable of the same sorts of things. Because data size and model size turns out to be a critical factor in this AI explosion and the success we're seeing of these models. Larger models give you better accuracy, they give you better generalization. The bigger is just simply better. The largest and most capable natural language processing model today is GPT-3, which was trained by OpenAI on NVIDIA GPUs, many of them, around 10,000 V100s, has 175 billion parameters. And that's just the beginning. We now expect we're going to see trillion parameter models and multi-trillion parameter models very quickly after that. Google has a hierarchical model architecture that they call mixture of experts, that allows them to kind of segment a really large model, and they've extended that to include the transformers, which is an attention-based neural network that has been extremely successful in the natural language world and is proving to be very useful and general purpose, extended to other tasks as well. Google has trained that to like 1.2 trillion parameters already. It's kind of hard to compare apples to apples, but these machine learning algorithms are also being used in recommender systems. These are those very large data footprint models that your internet service providers, your search engine, your e-commerce sites are using to create models of your choices, of you, all the choices you make, all your preferences, et cetera, and compare those, cluster you with others who have similar profiles of choices that you've exhibited in the past, and then use that to extrapolate and make recommendations about the next thing you should watch or buy or consume. And recommenders are also enormous and have some unique training challenges, like they want to be almost continuously training them to update them with the choices everyone is making. And then data analytics is really building very large graph-based models and mapping. It's also a component of recommenders, but you're basically mapping many entities and choices, et cetera, together in a very large sparse graph. And fundamentally, when you look at the requirements, when you kind of look at the training requirements, and there really are kind of two categories of hardware capability. One is associated with training, and that's extremely computationally intensive and requires really enormous footprint nodes that are, with really powerful matrix computation capabilities, very high bisection bandwidth communications with within this large memory footprint, and then very high system-wide connectivity to move data around among the models or the parts of these large models in order to exploit model parallelism. And some of that dedicated to provide very high performance storage. And when you contrast this with the prior generation of these CPU, these skinny pizza box CPUs that were being used to build CPU-only distributed memory clusters for high-performance computing, it's really day and night. So when you look at a node of a modern AI oriented supercomputer, there are many things that have changed. It's a big fat node. Our DGX A100 is our reference architecture for AI nodes. It's what we use to build our own internal systems and publish our results. It has basically 8 A100 GPUs. They're interconnected by NVLink, which is this extremely high bandwidth extension of communications that allows them to, you basically can program all 8 as if it's one big GPU. It's got a pair of high-end CPUs and a terabyte of RAM, but that's almost incidental because during training, these guys are just shoveling data and sort of orchestrating the presentation of training examples. And from a connectivity standpoint, it's as many high performance NICs and parallel planes of network as we can stuff in here. This box actually has the ability to have 10 Mellanox Connect X6 200 gigabit per second networks. And when we build systems according to this recipe we have that we call superpods for deep learning training, we use all 10 of those. 8 of them carry the communications between nodes, and the other 2 are dedicated to storage, so that storage communication doesn't interfere with data movements, doesn't interfere with the storage movements, if you will. So other aspects of this then are increased specialization of the GPU. And one aspect of that is support for reduced and mixed precision. And there are several interesting flavors of this down to 16-bit half precision that are important for training. And what these have enabled is then these special purpose functional units called tensor cores that basically give another order of magnitude kind of scale boost to these multidimensional matrix operations that really are the bread and butter of training deep learning, deep neural networks as we understand them today. So what this looks like, the performance boost you get from using tensor cores. So the black boxes here are V100s. This is all relative to a V100. The green is the A100 performance in each of these precision categories. So the V100 FP64, A100 is a nice boost over that. It's more than double, and part of the reason for that is we introduced actually double precision acceleration in tensor cores. So there's without double precision tensor cores, this would be about 10 or 12 teraflops, and it basically ends up being power limited at around 20. And when you go into the FP32, that's when you start using the full tensor core, and you can see the capability difference starts getting incredibly large. There's this sparse capability. It's essentially forcing weights during training that are approaching 0 to 0 and ensuring when that happens, you're basically able to double the throughput. But when you get then, notice this is 310 teraflops in that case, and without sparsity, 155 teraflops. And when you get to the FP16, The baseline is 310, and with sparsity, you're up at 625 teraflops in a single GPU, and there's 8 of them in one of these nodes. So, it ends up being, for half precision, a petaflop scale compute node. And then just as training can exploit reduced precision, inference, once you have a trained model, you can squeeze these things down without losing accuracy in most cases, and you can actually inference in integer, int 8. And so for very high performance inferencing, there's also a proliferation of low precision formats as well. So this is Selene. This is our internal supercomputer that we've built. NVIDIA does a lot of AI research, and it's helped us be competitive in a number of industries. So Selene is basically 4,480 A100s in 560 of these DGX nodes that I illustrated. So there's 850 of these 200 gigabytes, gigabit per second switches, 14 petabytes of storage. It's 2.8 exaflops of AI performance. So that'd be measuring this half precision rate. And so even though we're still looking forward to the first double precision exaflop system, there are already several multi-exaflop systems from an AI peak performance standpoint in existence. And so, yeah, this is number 5 on the top 500. So it's a serious double precision machine as well. It's number 1 in ML-perf, which is, all these training things. And we take pains to ensure that we're always number 1 in that. And this is the fastest industrial system on the HPL, but it also is extremely efficient. It's the second most efficient system in the world in terms of gigaflops per watt. And it's second only to a smaller version of itself. So that efficiency is really important in order to be able to actually access the very high performance. So something like this is coming soon to an area near you. NVIDIA announced, I think, a year ago that we were going to build this computer called Cambridge 1. This is going into a colo facility that's in Harlow. I'm not familiar where that is, but I don't think it's Cambridge. And so this is supposedly something like 20 miles from central London, but it's something that we're doing in partnership to enable partnerships with a number of both commercial entities and research organizations and funders, and also universities, presumably, with really a focus on healthcare, large scale AI, and enabling universities and startups to do some large scale work. So this is going to be 80 DGX A100s. It's almost done, as I understand. So this is a 400 petaflop AI system. So about twice the AI flops as Summit is double precision. So we have this amazing reduced and mixed precision hardware. Can we put that to work for HPC? Yes, definitely. Jack Ngara and friends have been working on using tensor cores to accelerate HPL, and there's now an AI version of HPL. And there's others who have worked on this. we have big data in science as well. And so, we can do all kinds of recognition and classification sorts of problems, like, training a neural network to detect extreme weather events in climate model outputs. It's being used in kind of the control cycle planned for ITER and other fusion power generation experiments to control plasma, using it to sort through events in the superconducting supercollider here at CERN. When that comes back online, its bandwidth is going to be doubled, and so hopefully we'll be able to filter more of the output more accurately. And it's also being used to control the adaptive optics in large telescopes, and maybe a little more famously, what is now being used to filter LIGO, the laser interferometer output, to allow detection of gravitational waves in something closer to real time. And all of these have either an accuracy advantage or a performance improvement that is pretty valuable. In this case, 5,000 times faster than the previous solutions, meaning that you can actually know that you're looking at a valid event in time to alert optical telescopes and radio telescopes to swing toward that part of the sky, and possibly be able to achieve this multi-messenger astronomy objective of being able to collect photons and try and correlate those with the gravitational waves. And those are all really interesting, but they're not solving PDEs and accelerating HPC simulations. So I'm going to spend the rest of my time kind of talking about that specific objective. In 2015, I saw this really interesting paper that was it was published as part of the SIGGRAPH Computer Graphics Conference, and it came to my attention in kind of a weird way. But basically what these researchers did, and they were trying to achieve visual realism, not necessarily be able to use it for scientific or engineering purposes, but they basically trained a machine learning algorithm using Navier-Stokes to, a traditional Navier-Stokes solver, to generate lots and lots of labeled training data to then approximate Navier-Stokes. And they achieved reasonable veracity to the much slower simulation at 3 orders of magnitude speed up. It was fast enough. It had previously taken them like 90 minutes to generate 30 seconds worth of simulation, and on a single GPU, they were able to, with their simulation, actually have it be fast enough that they could interact with these, large particle count, particle-based fluid simulation. So that was, when I saw that, it was really intriguing, and it made me think, made me go, I wonder if we could take other numeric models and use those to train neural nets. One of the big problems with training neural networks is having a well-labeled data set, and being able to use traditional numeric codes to generate simulation sample points that we know are the right answer, and then try and train neural networks to be surrogates for that solver, immediately seemed like an interesting interesting path to follow. And deep neural networks have been shown to be really universal function approximators. And you can kind of intuitively see that they have to be extremely capable when you look at many of the things that they've demonstrated, and you think about how you would even begin to approach writing a function that could do that. You can imagine that this learned model capability could be extremely flexible and capture a lot of interesting physics. So kind of the idea is, at least in part, if to either use real data to train a neural network and possibly even discover some physics truths, if not at least be able to encapsulate them in an inexpensive and efficient model, or to use, as I said, a numeric model to generate training data that can be used to train this surrogate model that then can be run in just inference mode. One pass straightforward. Inference is really fast, runs at basically peak performance of whatever hardware you run it on. A lot of inference is done on CPUs because once trained, it's just one forward pass. It's not an iterative sort of thing, and you have an answer, and that's sufficient for a lot of applications. So you can imagine that double precision could become really just the purview of simulations that are being used to generate training sets, and that you can be integrating simulation data with real world data. Kind of the workflow here is you reserve part of your data set to do regression testing, but you can see that the progression of precision required kind of trends down as you get to this inference point. And once you reach this point of having a trained model, now there's the potential of orders of magnitude speed up. So the big question has been, since 2015, when I first saw that paper, is, are ML models really useful for science? And George Box, famous statistician, this kind of captures the state of a lot of high performance computing, where people have hand created shortcuts where the calculations and the PD solvers are too complex to really deploy. And it's that gap between the practicality of solving the equation versus at scale to make a useful simulation, versus the ability to generate enough training samples to train a neural network that can then generalize sufficiently well over novel input data to potentially both. It's that gap that provides the opportunity for not only an acceleration in efficiency and performance, but also better accuracy. And so here's a really good illustration that arose in the quantum chemistry area and was the first iteration of it was published in 2017. What these researchers from the University of Florida and Tennessee put together was, basically they came up with a representation for molecules that and this kind of illustrates the problem. Look at the orders of magnitude down here. Accuracy is on the vertical axis, and DFT, what they're trying to do is solve Schrodinger's equation and calculate the energy, the total energy of molecules. Eventually you want to be able to simulate much more complex molecules and take them through all manners of chemical processes, et cetera. But the problem is, when you look at just the most efficient calculations, the accuracy is terrible. And when you try and drive up the accuracy, the cost in turn, this is a million times DFT, which is, kind of the minimum level of accuracy you'd like to achieve, is a million times more expensive than the approximations, and the gold standard is a billion times worse. What they did is they essentially used DFT to create 20 million sample molecules using up to 8 atoms from a database, and then tested it on total energy correlation. The black line down the middle is DFT, and then the red plots represent novel presentations of molecules, and comparing the DFT results, which are on the black line, with the estimates from this neural network. So not bad. And this works up to molecules that are significantly larger than they could afford to compute prior to that. They went a step further a couple of years later by using this coupled cluster method that is a billion times slower than any one, or than this the most naive and fastest approximation. And they did something that's called transfer learning. It's too expensive to generate 20 million examples using CCSD. So what they did is they took they trained a new version of ANE1 on 5 million data points, then essentially use that as a starting point to tune the training with another 500,000 data points that they more affordably were able to generate using this coupled cluster method. And this is DFT accuracy, and you want to be on 0. And this is this new trained version of ANE. So really achieving DFT accuracy maybe a bit better, and still, in this case, it's like 5 orders of magnitude faster. And so these methods are being pursued very vigorously for molecular dynamics, are part of the story of the rush to look at potential mitigating compounds for COVID, et cetera. Let's switch to something completely different and talk about Earth system models. By the way, I just want to note, I'm giving some links here to talks. We just had our GTC conference. We do this every year. This time it was all virtual. I'm hoping a number of people in the audience were aware of that and registered for it. All of the talks were recorded. It's an amazingly good conference, and you can find these talks, and I'm highlighting talks that were really interesting and chock full of content. In one more week, they're going to be moving all of that content to something called NVIDIA On Demand, and it'll be available to people who didn't register for the conference. So after we're done here, I'll try and make the links for the things here available. But one of the biggest problems is just for predicting weather is modeling both the large scale dynamics and all the small scale physics issues, and the filling in the gaps and normalizing just to initialize the model. All these things are very challenging. So just a couple of quick ones. Here's one that's just doing nowcasting, basically looking ahead like 8 hours. And it's this one, Google published this was trained purely on radar data. And so, and actually beating conventional models in terms of accuracy. These researchers first published a data set that could be used to benchmark medium range weather forecasting. And then they basically did some testing of it and determined that it was actually possible to beat, with sufficient training data, numeric models for medium range forecasting, again, based purely on using image data, multi-spectral satellite inputs, et cetera. And even creation of those models from these multi-instrument eyes in the sky, so infrared and microwave satellites collecting data about the globe, and then turning that into a set of inputs that can go into a Earth system modeling model. Used to take 2 hours to process one day, and they got a 1,400 times speed up by training a neural network to do it. And finally, when you're doing climate, one of the problems when you're looking back in time is that you have very spotty coverage of measurements. And so from the image processing AI world, there's these techniques that can in-paint basically extrapolate and complete pictures based on very spotty missing data. And so they're using those techniques to reconstruct missing climate information going back in time in the records, and really are enabling more accurate looks back at the Earth's climate than were possible before. So just to talk a little bit about challenges. So labeled data, pretty much all neural network, not pretty much all, but it's supervised training. So you need to have accurately labeled data in order to train a neural network. Some of these challenges are addressed by design when you have a synthetic, like a numeric algorithm that is generating your data set for you. So not having a lot of data, observational data from the real world, and labeling of that data becomes a non-issue when you have numeric codes that are generating that. And then other questions about, can we really believe the predictions? Is it giving you results that actually conform to what we know about science? These are more troubling, but there's a lot of really interesting work, and that's the last two examples I'm going to show. The rest of these are kind of, how can we plug this capability into existing codes, and what happens when you run large numbers of ensemble simulations to try to do predictions. And I don't think that one particularly is unique to AI. And then, are you overfitting? Is the model you're training capable of generalization? And I think we have some really exciting and good answers for these capabilities, and I'll illustrate those now. So people have been trying to enforce physics by making sure that the data set that you're training to, by kind of looking at the output and then still punishing the neural network, even if if its output violates the laws of physics. Recently, people have been taking an architectural approach where you're actually using the partial differential equations that you are solving to generate the training set, and you're using that error from the PDEs itself to determine the training error. And so this is a way these physics-informed neural networks, or PINs, has turned into a very hot topic, and has demonstrated that it can supply very accurate and very fast and efficient answers. This was a seminal paper. This is just a good survey talk from GTC, but this particular paper by these guys is much cited in this world. And NVIDIA, being who NVIDIA is, looks to take things like that and turn them into tools. So we are working on something called SimNet, which is a set of tools that allow you to fairly easily define and train and then operate physically informed neural networks. So training time is still long. This particular heatsink simulation took like 4 days to train on a single old V100 based DGX1. But once you've trained it, you actually have the ability to vary parameters and get updates to your simulation in real time. And so you can see there's some sliders that allow you to vary some of the geometry of the heatsink and instantly see the changes to the simulated temperature profile and the velocities in the stream, et cetera. So this is already available in an early release. You can go to developer.nvidia.com and sign up for early access. And we're using it already to evaluate future current and future heat sinks and its accuracy and its speed. Because of the ability to vary parameters after training and how fast that proceeds, it really is good for engineering because you train once and then kind of play with the dials to evaluate heat sinks and the like. This is great for optimizations. It's also being used, and there's a couple of interesting talks there as well to look at medical data and extract then information. This is an aneurysm in somebody's head. And basically what they're doing is taking MRI data about the flow and then inferring what the stress is and kind of the pulses that are straining the elasticity of the aneurysm in the veins might be. So really, really amazing things. And the last thing I just want to walk through is something that's brand new. There was just an article in Quantum magazine about this, as well as MIT Technology Review. This is work that was done by researchers at Caltech and NVIDIA. Anima and then Kumar is director of AI algorithms at NVIDIA in our NV research organization. And what essentially this Fourier neural operator does is it learns a mapping between functions. And so rather than kind of learning that discrete noisy data, it's actually learning the function, the PDE function itself. And so even though you might train it on a very low resolution data set, because it extracts the function essentially, you can change the resolution of the simulation without having to do any retraining. So something that the researchers call zero-shot super resolution. And this enables you to scale the simulation. This is brand new, so this is only 2D, but they're working on it in a number of different areas. They've shown that it helps capture the trajectory of chaotic systems much longer than previous attempts. This is kind of the error map, if you will, as the chaotic process proceeds. And they're using it to model plasticity. And here they've changed the thickness of the material without having to retrain the FNO, and it's generating accurate and 10 to the fifth faster results. I think the final example is just modeling in this case ultrasound of a liver with blood vessels, and the remarkable thing is because the trained neural network part of it is in the frequency domain, it's able to capture really both large granularity and small granularity details that other methods really are incapable of. So finally, what is this mad potential? Is it real? And what are the attributes of it that I think are really worth highlighting? First of all, better simulations. If you can get better stability and accuracy out of these methods, this is a way of carrying us. All of these are in service of carrying us forward in this post-Moore's law world that we are driving at high speed into. So really, the whole point of this is to resist Moore's law fade, and this is accomplished in part by not requiring double precision everywhere. The physical measurements we take of the real world are rarely to 64-bit precision. That precision is mainly required because of round-off errors of the numerical methods. And so this means that both we can accelerate computation, but you can store more data points in a certain amount of memory as well. And that means you can afford to hold larger data sets, larger models in memory. And as I said, once you've trained these things, they run with a single forward pass at peak speed. So you're able to accelerate conceivably existing applications without restructuring those if you're only using those existing applications to generate training data sets. And the inference time is kind of independent, and the model complexity is independent of the veracity of the science that you're using in the simulation you might be using to generate the training data. In other words, you can incorporate much more difficult calculations in the creation of the data set, and it doesn't really change the inference time by very much. So instead of seeing these n² explosions in runtime as you change your model, you can get better science at low incremental cost. And then reduce code optimization requirement. If scientists are writing their equations in natural ways, and the main thing that's going to be done with those is to generate training data, this lowers the bar for getting this huge acceleration that you might achieve over trying to directly accelerate that simple code you might scratch out on the whiteboard and try and type in. Just because you're not trying to scale and deploy that code, similar to the DFT versus CCST example, you can do far less computation to generate the training data set than the actual full-scale simulation. And then this is kind of an example from Google. Reduced maintenance cost. The applications, traditional applications for science, if you look at the Gaussian and Amber, a number of different applications. These are large codes, and it's expensive to change them. Weather codes, it takes many years and a lot of effort to change them. Google cites these statistics about their translator. They had this multi-language translator that they had used until 2019, I believe. and it was around 500,000 lines of code and very expensive to maintain. It's based on non-deep learning techniques, and they replaced it with a data trained model that's all deep learning. And basically that's some 500 lines of code plus terabytes of language samples. But the maintenance then of that code is almost nothing. It's really about curating the data. So in the end, the bottom line is these orders of magnitude speed up and lower energy. And that's the final goal from the perspective of a luthier trying to generate good guitars for science virtuosos. And that's my last slide.
Wonderful. Thank you very much, Steve. Okay, so now we've got a few moments for questions. If anybody wants to ask a question, please raise your hand or type in the chat window if you prefer. And I'll read it out for you.
May I jump in? And first of all, thanks, Steve, for a really wonderful talk with such a science perspective tied to your incredibly interesting compute company. Of course, I cannot resist to ask you if you would say a few words about comparing the sort of up and coming accelerator industry, perhaps first led by the TPUs from Google, with the NVIDIA product line.
Right. Well, so there have to be at least 50 startups that are, and some of them now really well funded. Just in like the last couple of weeks, I think there's at least 2 of them that have gotten multi-$100 million funding rounds completed. GraphCore, I think. I'm trying to remember the other one. Intel and AMD are really stepping up the effort on the GPU side, and even people who are today our customers like Google, who use our systems heavily in research and host them in the cloud for others to use. Have their own architecture efforts, their own chips and special accelerators. And I think it's great, and I welcome the competition on the hardware side, but that's really, the hardware is just the chips and the accelerators and the hardware. It's just a tiny part of the value that people get from the whole platform that we provide. And NVIDIA has far more software engineers than hardware engineers, and we have several millennia invested in the software stacks and the libraries and the tools that are now part of this whole pretty much mostly free software ecosystem that supports researchers who are trying to train at scale, trying to be creative with neural network architectures, et cetera. And that, trying to match that, trying to do more than just train, ResNet 50, or AlexNet, make claims about your underlying hardware performance. Trying to actually use these things across the scale and the spectrum of research areas, it requires that full software stack. And I think the trajectory, having been in a startup myself, I believe it's likely that most people in those startups are hoping they will become acquisition targets eventually for someone like Intel, who is at least a couple years into the effort of creating the software stack necessary. And I think that without that, these are going to be very specialized and niche devices, and it's not easy to find some trick that is going to accelerate matrix multiplies in some super remarkable way that's going to outweigh the all of the other layers of the value proposition that NVIDIA has created, including the software and all the way up through systems architectures, et cetera. And so I think it's going to be a while before that competitive landscape really changes a lot, and NVIDIA is going to continue to innovate. A lot of startups had to completely reset their business plan in 2017 when VOLTA was introduced with Tensor cores for the first time, because it basically blew away the secret projects that they had underway to try and do the same thing. So that's, I guess,
It's a great answer. Yeah, thank you.
Maybe if I can continue along the same lines, what is your sense looking into the future? Are we going to see a lot more specialization on the hardware level? You've hinted a bit at it, during your talk. Is there a market for sort of ultra, maybe even application-specific hardware, or is most, let's say, of the value going to be at the software level?
Well, I think it's going to follow an arc, right? So, you can at some point, and I don't think we're at that point yet. We're probably quite a ways away from that point. But at some point, deep learning is going to, the rate of change and how much experimentation is going to stress the underlying architectures in pursuit of different learning algorithms, different neural network architectures, different model architectures. Those algorithm advances require kind of general purpose, quote unquote, general purpose hardware. It's a little ironic to be talking about GPUs as being more general purpose than the alternatives at this point, given that just a few years ago, they were considered very specialized and CPUs were the general purpose devices. But there's, it's possible to get a whole lot more specialized, but I think that requires that, there's some kind of universal convergence on the algorithms that you're going to want to kind of set in stone, so to speak, set in silicon, and that happens, and we do this on GPUs, right? We used to do GPU acceleration of video encoding and decoding, and now we have little ancillary blocks of transistors that just do H.264, and JPEG, and the same is true of video transcoding, and there's a DLA. It's basically an inference block that is, and you can gain another multiple in efficiency by having, by basically translating something that was programmed into something that's just now basically an ASIC block, right?
Yeah, I see. Thanks.
So I think it'll happen, but not yet. And I think when it happens, that we'll probably treat it like H.264, and there will be those blocks will be dropped on GPUs as well.
Yeah, I see.
There is a lot of excitement about software technologies to enable DSLs, like the multi-level intermediate representations, MLIR, compiler technologies that make it easier to target unique hardware. And I think that is going to be promising and enable more specialization. But there's still the larger ecosystem is going to kind of constrain how wildly specialized hardware gets.
Right.
I think.
Right. Thanks a lot. Okay, Greg, you've got a question. Please go ahead.
Hi, thanks. Yeah, thanks for such an interesting talk. You've given us a lot to think about. One of the things that you, I think, were saying was that even in this new paradigm, there's a sense in which the more units you have, the more you can do. And you showed your sort of souped up machine with all those GPU arrays.
Right.
There were a couple of seminars earlier in this series where I won't claim to have fully followed what was being said, but there was some sense that was being given that if you had a network that was wide enough and deep enough, then you might be sort of starting to get to some sort of continuum limit or thermodynamic type limit where, there were so many parameters that you could, that maybe getting more and more of them started to become less useful. So I was wondering whether there was any sense in some of the applications that you were talking about at the end,
Right.
where at least for some problems, you might have seen some sign that that you wouldn't need more, that this sort of voraciousness for ever more computing power, at least for some types of problem perhaps, might actually have an endpoint where you could run some kind of problems and you had enough computing power and that was it.
I think there's a couple of forces that at work in the direction that we would like, which is to try to at least constrain the compute cost required to train giant models, and hopefully even make models more efficient so that the size of the model is you're getting more bang for the scale of it, right? If you look at scaling up some of these image recognition networks, as you scale up the number of parameters, the number of percent that you improve recognition accuracy, it tapers off. But this is, as you say, these are kind of comparing like fixed architecture networks, and that's not a good way. Just scaling horizontally, if you will, is not, in my opinion, an optimal way to expect things are going to go. If you look at scaling strategies in almost every other paradigm, hierarchical organization is really much more efficient than flat. If you think about organizing a team or military or a company, if you think about and we did this even controlling clusters. If you think about trying to boot lots and lots of servers, having some hierarchy to the boot masters, if you will, allows much more efficient scaling to very large numbers of workers, if you will. So I think that architecture tactics like Google's a mixture of experts and their more recent switched transformer hierarchical model, I think that's going to be the future. I mean, that's how our brains are organized. We have a lot of hierarchy in our own internal nervous systems. And so I expect that's going to play a role ultimately. I also, we see this often. We see papers where essentially people have figured out something about training and training algorithms, and it's in a number of different parts of improving how these error surfaces are traversed, and how how things are pruned or initialized or whatever. But algorithmic improvements are making as large of an advance over time in terms of enhancing performance and increasing the rate of convergence and making training more efficient. Those algorithmic improvements matter more than the hardware changes, the hardware improvements, and it's hard for me to believe that stochastic gradient descent and backpropagation as we have it today, that this is the pinnacle, that and there's a lot of research going on in few shot training and transfer learning and the like, that I think is going to make training a lot more efficient. Also, we don't have to always start from zero. The notion of taking pre-trained models, and this has been shown to be really productive in natural language models, to take a general purpose translator model that might have taken really big system weeks and weeks to train. That same model with a much smaller data set on a much smaller system can be tuned to add an additional language at just a tiny fraction of the cost. And so NVIDIA is making pre-trained models available in the natural language area and in the recommender system area, and specifically to try to make the cost of training the model initially less of a factor in people adopting the technology. And so I think things like that, approaches where we're not starting from zero, hierarchy, improvements in algorithms, and improvements in hardware and software as well, are all going to be factors that will help help researchers who don't have something like Selene in their organization still make contributions to the field, and for people to deploy in real applications these technologies in a more affordable way.
Thank you.
Fantastic. Thanks a lot. Okay, I don't see any more questions. Last call for questions. If there aren't any, well, then let me thank you very much again, Steve, for giving this talk,
Sure.
for trying a second time.
Yeah, I'm glad things held together.
And for getting out of bed very early again. Thanks a lot, much appreciated.
Yeah, thank you very much. I really appreciate the opportunity to take so much of your time.